after this problem setting, then we move to the another domain, which is designed for continuous actions. So how we can develop or derive the policy parameterization for continuous action. For this continuous action space, actually, as I mentioned, the continuous action space is quite general or normal action space in real world applications. Like you control your autonomous vehicles, you control drones, you control different kind of robots, machines, different kind of sensor information. Their actions are continuous. So for this kind of purpose, we can design the policy pi in the form of normal distribution. Okay, we just use the normal distribution to represent the policy pi. So if we consider, so in this normal distribution, usually we have two parameters, mu and sigma. Okay, mean and standard deviation. So if we represent the mu and sigma with the linear combination, linear function of the input feature vector, so then we can have a very concise shape, as I showed you in the last lecture. You can kind of derive very concise shape for the updating. Okay, so this is for what we learned, the main knowledge what we learned in the last lecture. And so we're gonna have our quiz. Okay, now we can open the iCampus, or I will turn on yeah. So it hasn't been any. So we'll start the quiz from 12:15. Okay, so you can the quiz, the thread will be available from the 12:15. So you can open. Okay, yeah. Once it's available, it will be open. If you didn't bring your laptop or the pad, you can use your smartphone to scan. So during the quiz, you should not check other materials, okay? So yeah, please refresh the quiz link, then you will see it. I already opened it. Okay, so yeah, I guess this is the last time we review our reinforcement learning framework in this semester. So as you may see here, we have been working on this framework then again and again. Initially, we introduced the different kind of settings, how to learn the policy, can be the value-based or can be the direct policy learning, right? So we design, so the agent is like a brain for completing some tasks. And it has a policy to decide the action based on some states. Then later on, we parameterize the policy with theta, so we can learn the policy through the updating the parameters theta. Then most of the time we spend the efforts or like energy on the state value function and action value function, which represent the traditional or standard approach for the reinforcement learning. Mostly it's based on the Bayes equations. And after that, we try to parameterize both functions. So then with the parameterized functions, then we can use like other approaches by combining like linear functions or neural networks, nonlinear functions. Then we also introduced the eligibility traces, which include two parameters, lambda and z vector, okay, which can switch the forward view to the backward view. So previously we need to wait several steps to update the previous state. Now we can reverse this process. We just stand at the current state, and based on the history, the data, then we can update the current state value or action value. And in the last lecture, we learned how we can approximate policy directly from based on the policy gradient theorem. And we develop multiple approaches and methods. Okay, so generally we follow. So mostly in the practice, so we combine. So we did in the quiz, so we combine both the state value function and the policy gradient method together as a AC method, right? So we use this both policy approximation and state value function approximation together to learn a better policy for the agent to interact with the world. So we can also combine, if you have a model, we can combine the model planning with the Dyna or Dyna-Q algorithm together. So you may have multiple components in the agent. Okay. Then if you update for example, for planning, if you update the state value, you update the state value function. If you want to do the control, update the policy based on the action value function, then you update the Q. So this is the iterative process, what we learned. And we also, most of the time, our objective is maximizing the expected return. So in the last lecture, we shift a little bit to maximize the performance of the policy. Actually, the two objectives are related, and they just like a little bit. So if you remember, when we derived the policy gradient theorem, actually we derived it from the state value. Okay, state value we use V, the S0. Actually, we derive the state value based on state value to derive the policy gradient theorem. Okay. Now we look at this tree for all the approaches we have learned. So, for example, if you meet some tasks or some problems you need to solve, so you may need to decide which approach you need to use. Okay. So the first one is that on the top, the root, can we represent the value function with a table? So whether this is tabular tasks, so we can design the state value function or action value function by the Bellman equations. So if it is yes, then we need to check whether it is a continuous problem or just episodic problems. If it's no, then we just need to check again for do we have a model. So we will look at this the other side, yes. If it is a tabular problem, if we go in the next page, we will check. The first one, we check if it is not the tabular problem, then we need to ask, do we have a model? What is the model? Model is the description of the environment. It will provide some dynamics stuff to your agent or to the environment. Then if it is yes, if we have a model, then we need to decide whether it's prediction or control problem. If it's control problem, then we can use the value iteration, policy iteration. We learned at the beginning of the lecture, maybe in the week 3 or week 4, we learned this value iteration, policy iteration. Means like for the grid word, right? The grid word is like a model for us, if it is model. And if it's a control, if it's prediction, then we just want to predict the state value, then we just rely on the iterative policy evaluation approach. We learned the iterative process, right? Then move to so this is branch for the problem heavy model. Then the other branch is if we don't have a model, then we need to ask whether we want to learn a model or not. If we want to learn a model, means that we can do the planning, right? We do the Q planning. As you remember, we can use the TD learning or Monte Carlo process and the unstep TD, different kind of approach to the real time, the online learning. Then at the same time, we can also do the planning based on model. So we can learn the model based on the feedback rewards received from the environment. Then we put into the model, we learn the model and update. So we can plan multiple steps in the model and feedback to the action value or state value function to decide to improve their performance. Then we also had the DynaQ and DynaQ Plus. So it's just the implementation of the planning. Okay, and DynaQ Plus is the one because DynaQ sometimes fail to discover some changes of the environment. So we introduced the DynaQ Plus, which brings the bonus reward to some actions which hasn't been tried for a long time. As you recall, okay, the plus means that the bonus plus. If we don't want to learn a model, then we need to ask another question. Learn on each time step. So whether we want to learn each time step, actually divided into two groups, whether it's Monte Carlo or it's like a TD, right? If we want to learn on each time step, then if it is yes, then we rely on multiple approaches we learn. Whether now we also every time at the end we need to ask whether it's control problem or the prediction problem. If it's control problem, then it linked to the Q learning, expected SARSA, and the SARSA. Okay, these several approaches we learned. If it is just prediction, we just want to update the state values, then we use the TD. Okay, this is the approach we learned. On the right-hand side, if we don't learn this process on each time step, then we also need to ask whether it's control or prediction. If it's control, then so as you may see here, all the approaches are MC, right? Monte Carlo method, because it is not learned based on time step. So at the end of the episode, we update, okay? So if it is control, we use the epsilon soft MC or the exploring star MC. If you recall, the ES exploring stars MC is that we bring the exploration to the MC. So just in case, because MC may just each time just greedily select the action. So we give the small probability for every the action, then can have the chance to choose those non-greedy actions. The absolute soft MC is that we design or derive the probability a little bit different. So it's like we divided the greedy action group and the non-greedy action group. So we give the non-greedy action group the epsilon 1 divided by the epsilon, and then epsilon divided by the number of the size of the non-greedy action. Then for the greedy action, we use -1 minus epsilon divided by the number of the non-greedy action. Okay. So on the right-hand side is the no. If it's not control problem, then it just comes to the MC, the standard MC prediction approach. So we just update after each episode, then we update the state value. Then it also linked to the off policy. So off policy, in this off policy MC, we introduced the important sampling ratios, right? Important sampling ratio. We use the behavior policy, and we need to re-architect or rescaling the behavior policy to the target policy with the importance sampling ratio. Okay, we just put that ratio in front of the return, and we can we can run both policy together. So this is off policy MC. So this is what we learned. Yeah. So Now we move to the left-hand side. If we can do a table. So now the first question is we need to ask whether we are using the average reward. Are we using average reward? So averaging reward means that it's a continuous problem. If we are using average reward, means that it's a continuous problem. Then we also need to ask whether our action space is continuous or not. Okay. So if action space is also continuous, we use the Gaussian AC as we designed in the last lecture. So we design the policy become a Gaussian normal distribution, right? So the action space, the policy become a continuous distribution based on the Gaussian. And at the same time, the GT, the return will also be based on the average reward. It will be the so-called differential return. If it's not the continuous action, then we use the softmax AC. The softmax AC means that the policy is defined by the softmax. Okay, and the differential semi-gradient salsa. If you recall, the differential means that we are using differential return for the parameterized salsa. Okay, it's not designed for the continuous actions. On the right-hand side, if it is no, means that it is not designed for the continuous tasks, right? It is for the episodic task. So which means that it will have multiple episodes. Each episode has a terminal state. Then we need to decide whether we will learn it on each time step. If it's yes, then it just comes to our we learn those most of approaches are from this area. Whether it's control problem or the prediction, if it's control, then the SARSA, Q-learning, expected SARSA are the approaches we learn. If it is just a prediction, then we use the semi-gradient TD to do the prediction. If we don't learn our each time step, then it just becomes the gradient MC. Okay. So actually, since we are considering here, do we have a table? Actually, the gradient or semi-gradient TD can also be parameterized in the way of tabular case, because if you remember, I showed you if you use the one hot vector for the gradient MC or semi-gradient TD, they are just the case of the tabular case, the tabular problem setting. Okay, so this is like a big picture for those approaches we learned in this reinforcement learning. Yeah, for this tree, for this big tree, any questions? Yeah, so in the last lecture, we learned this softmax AC, Gaussian AC for the continuous. Okay, so yeah. So yeah, so this is kind of summary for what we learned in this course, this semester. So then we move to next. So today we're gonna particularly take a look at two applications. The first one is the deep Q network. The other one is the deep reinforce with the network, right? With the neural networks with the nonlinear function approximation. The first one is the deep Q networks. So as you may recall, we learned the Q learning, right? The first version we learned for the Q learning, we use it's like a tabular case. Then we can represent the action with some probability. Then you can build the table. So you put the state and action, put the Q learn the process. You update the reward. Then you can update the Q value, the quality of the action, right? Based on the Q value, then you can make select which action you need to use. So if we extended it to the like a nonlinear approximation approach, for example, we use a neural network to approximate those parameters inside of a Q network. Then we have this deep Q learning, okay? How it works, so we give the input, the state. The state can be multiple sensor information, then sent to these designed like multi-layers neural networks. Then it will generate the action value. So Q value action, 1, 2. So it's like generate the predict or suggest the which action will have a, so each action will have a Q value, right? Some action will have a higher Q value, some action will have lower Q value. So then you can decide, select an action with a higher Q value. So this is the comparison between the tabular Q learning and the deep Q learning. So for example, if you have this this environment, so on the left-hand side, so we can use if you have images, for example, this game, the Atari game. So we can directly use the images for learning, for decide the policy, for decide the Q values of the action. Then we use multiple frames of this action, this game. So each like a frame has one action, right? So we put into the convolutional layers. So it will generate multiple features for these frames. Then we put the fully connected layers. It will generate the Q value for multiple actions, left, right, and shoot. So means that actually this is your agent. Then you need to left or right or shoot your gun to eliminate those monsters, right? Aliens. So this is generally how the deep Q networks works. But the thing is, if you just directly use this way, actually there are a lot of issues. It will not work well because naturally the reinforcement learning or the Q networks, they kind of have some unstable instability issues because they will kind of diverge to some other area, not converge to the optimal solution. So this is mainly from those nonlinear activation functions. Okay, so before we try to solve those issues, we first need to pre-process the input. So the input, as you may see here, the input are the images, like some pixels times some resolution images, right? So original image will be like 160 times 221, and with 3 RGB, with colored, right? 3 channels. Then we can pre-process it to reduce it to like rescale the pixels, right? To remove those, try to reduce the size, then it will kind of improve the learning efficiency. And also we introduce multi-frames instead of using one frame. So here the 3 means that the 3 RGB channel, but here the 4 means that the 4 frames to exploit the temporal information from this game. So it's like we need to compare whether we have this the move of the action actually where it goes, right? So yeah, as is summarized here, we reduce the state space to the 84 times 84 and the grayscale it. Okay, without color means that we reduce the 3 color channels to 1. Then we stack frames. Then each is processed. The stacked frames will be processed by the 3 convolutional layers, CNN, right? 3 CNN layers. Then, so these 3 layers kind of can capture multiple information features inside of these frames, right? We can capture spatial relationship in the images, like multiple components, the aliens and your spaceship, and those kind of relationship. So you move left or right, then you're shooting your bullet, which alien you are shooting. Those information can be kept, can be learned from the CNN. Then we also need to keep the temporal property, because as you may see here, this is another game. So if you just learn based on one particular frame, actually you don't know whether which moving direction of this ball is moving toward, right? It can move to this direction, can move to this direction, but we don't know. So we need to use multiple frames. For example, if you from here, you will clearly see the frame 1, 2, 3. You will clearly see that this ball is moving toward the right-hand side, right? Move a little bit, a little bit, a little bit to this side. So you will see what is exactly happening there at the action. This is why we need to use multiple frames in this deep Q networks. Now we can just parameterize and use the neural networks to run our deep Q networks algorithm. So this is the original, the Q learning, the approach we learned, right? So actually here it did not do the parameterization. Like, so the Q should have a theta to it should be in different settings. In our case it should be W, right? W, the weight vector, to parameterize the action value. So as you may recall, the Q learning, so we have a reward plus discounted maximized the action value. So here when we call it this off policy, because this will select an action based on the maximum Q instead of based on the policy. So the minus the previous Q value, so it's like serves the TD error. The whole value serves the TD error. Then we update the previous. We add to the previous the Q value. Then we update the new Q value function. So now we can generate the target and loss function if we use those. The target is as is shown here. We use this reward and plus this discounted maximum Q, maximizing Q with the action, and with the target. Then we use the loss function, which is the square root loss function, squared loss error, right? So we just use this yi minus the Q to decide whether so each time we will have a new data, then we just try to minimize this the loss function. Then we can do the gradient. So we do the gradient to this loss function. Then the gradient will be on this Q. Okay. So actually we derive this form in our parameterized back action value the process, right? So we put this gradient here, and the Q learning approach will be here. So here you use theta in the lecture we use the W, right? It's a little bit different, but yeah, the process is similar. So the target and the Q loss, what do we need to do? So now the training phase. Actually, we have two phases. The first one is the sampling. We perform actions and store the observed experience tuple in replay memory. Here we introduce the replay memory, so we will talk about it later. And training, once we have this sampling the data, the sampling data will be like a tuple, like you have the state, action, reward, and the state, action, reward. So those kind of tuples, multiple tuples. So it's like you run your simulation, then those data will be accumulated, right? Then we just select a small batch of tuples randomly from those samplings, from those samples. Then we use the gradient descent to update the theta. Here is theta, in other cases W. So as I mentioned, that this deep Q learning training may suffer from this instability, which is caused by the nonlinear Q value function, which is inside the neural networks, because in the neural networks, we use the nonlinear activation function, right? Like ReLU or 10H functions. Then there's also, because we are using bootstrapping. Bootstrapping means that we are updating the target based on the estimate, based on the previous estimate, because Q learning is a learning step by step, right? So each time we have a new reward, new information, then we update the TD error. So, but the TD error actually is based on our previous estimate. So there's a bias there because of this TD error. So these two reasons brings the instability to the deep Q learning. Okay, so since this is, if you just use native deep Q learning to some task, most of the time will not work because of these two issues here. Okay, that's why in the 2015, then the team from a team proposed their work. So they especially introduced the two tricks, let's say. So usually in the deep learning, we have a lot of tricks. So here we have two tricks here. The first one is experience replay. So in 2015, a team they introduced, because if you directly use combined deep learning, like CNN with Q learning, most of the time it will not work. Then we put this replay buffer here. When we talk about this replay, experience replay means that the reason we want to put this replay is that because this is online, the TD error is online, the step by step, right? So once we update one step, so actually in the next step, the previous step information we already lost. We will not save those information. But since the deep learning for the CNN, the large volume of data is helpful for better approximation. That's why we put those data, like when the agent interact with the environment, it gets experience state, action, reward, and next state. Then next time we get them again. But we don't save them. So those data are just wasted. Actually, we can reuse those data as the input for the CNN, right? So if we try to avoid this forgetting issue by also we can reduce the correlation between the experiences. So also this correlation issue is another very kind of usually when we try to learn some good policy, we want to have like exploration and exploitation. We want to explore the environment. We want to have a kind of different kind of experiences, right? But when most of the time when we make the agent to run, so it kind of most of the time it will experience very similar correlated states. So if we put those correlated states together to learn, actually most of the time the efficiency is quite low, okay? And also the result is not good. That's why we also try to reduce the correlation. And in the deep learning, most of the time we use the cross validation, right? When you have a data, then you divide the multiple mini batches, and we reshuffle it. Then we get those mini batches to build the training data and all the testing data. Then in this case, we try to reduce those correlation issues. So the data, try to remove those. Sometimes the training data has higher correlation, then we just remove those issues. Here we also use, so that's why we designed this replay buffer that saves the experience samples that we can reuse for the training, right? So it means that all the history data that we have a size of the sample, then for those data, then we can use it for training the CNN. Another trick is that we use the fixed Q target. So the current, if you just update the action value, the Q value, let's say Q value. So every time actually you need to update. But the thing is, sometimes those the target from the target and current Q value has a very sometimes a big difference, sometimes a small difference. So those also the current the Q value is estimated based on the previous step or previous experience, right? Actually, it may have some correlation based on with the current data. So in this case, the correlation between the target and estimate kind of reduce the learning efficiency, okay? Because if you just have the like let's say homogeneous data, then the learning you don't have a new information for your CNN. The update, the parameters updated there will not have a good like expressive power or the feature representations, right? So that's why the solution or the trick here is that we can use a separate network with fixed parameters for estimating the TD target. So it means that we will maintain 2 Q values, okay? 2 Q value networks. So we keep updating one Q value this network. Then we periodically use the parameter put back to another Q networks. Then when we generate the final result, we use those non-frequent updated Q networks to avoid the correlation between the current estimate and the target and the current estimate. Okay, it's like it's a kind of concept of the skipping, right? So kind of after multiple steps, then we update. We don't update every time step. We just remove those the relationship or the close relationship among those time steps. So after several steps. So here, as is mentioned here, we copy the parameters from the Q network every C steps. Then to update the target network. So the target network will be used to generate the policy, the output. Okay, so with all those the two tricks here, then we can design the DQN algorithms. So generally we have the sampling and training process. So actually, when you look at these algorithms, so these algorithms is written here in the one algorithm, but when we implement it, we need to actually split different components. For example, the sampling should be one function, the training is another function, and this fixed Q target is another function. So we need to use another data. Like here we use this Q hat to represent. Then this experience replay is another function. Okay, we need to save the data to another function. Then there's a main process. So you just call all those functions and run update the parameters, the theta, which is here, the theta. So in detail, when we look at here, this is we introduce this target action value function Q hat with weight is a Q minus equals Q initially just equal. Okay, so this is target, the one we're gonna update every several steps, not every step, right? So the action value function Q will be updated every time step. The Q head will be updated based on some steps. So as you shown here, every C step we reset the Q head with. So we use the latest estimate to update the target, the Q networks. So in the training process, we use this Q head, okay, Q head to generate the actual the value, the target value yi. What here is yj. Then we use the gradient descent step. You can use different optimizer You can add them or that in the PyTorch or any TensorFlow or Keras, they have multiple optimizer. So most of the time, we don't use the SGD, native SGD. Most of the time we use the Adam or I don't remember the IM props. Yeah, those kind of the optimizer. So you don't need to write the gradient descent step by step by yourself. We can just specify in Python. You can just specify the optimizer there for you. Then the network this means that it will do the back propagation stuff, like similar to the back propagation algorithm, and update those parameters, which is theta here. Okay. Yeah, experience the replay buffer is designed here. Store transition. So every time step, so we sample the data, then we save those data into D. D has some kind of size. With that size, then we sample random mini batch from the transition for the training. So instead of using the real time, because in real time, each time step we just have one time step, right? We just have one tuple of data, which is here the phi t is the state, at is the action, reward, another state. So this is tuple. Each time step we just have only one this tuple. But if you save all those history data into this D, then when we do the training, actually we use the mini batch from this D. Okay, it's like cross validation. We divided this D into multiple mini batches. Then we just select them for the CNN training. And with that, we can have a better. So it's like you do the again and again, and the theta will be improved gradually. Okay. This is the DQN algorithms. And so some of you in your term project, you propose to use this DQN for some tasks. So if you just use the existing approach, I mean the native the DQN without the fixed Q target and experience replay, most of the time the pulse will not be good. Okay, that's the issue caused by the issue here, nonlinear Q-value function. In the neural networks, we kind of altered the relationship between the input and output, and also bootstrapping the bias introduced in the Q-learning. Okay. Okay, let's take a 15 minutes break and come back. Okay. Okay, let's resume our lecture. Okay. So yeah, let's move to the next topic. Cut pole example by reinforced or inverted pendulum. Okay. So actually this cut pole, okay. Okay, so cut pole example by reinforced, or we can say the cut pole is also another version of inverted pendulum. This cut pole example we saw I used this as the example to explain some the concept. Okay. Overall workflow, if you understand the purpose, right? So you have this environment or agent, then your goal is to make this pole upright, standing here. Okay, keep standing here. So, but it need to fight against the gravity, either left or right. And there are some sensors. Here is some position and the speed, left or right speed. Right, speed, the velocity has the direction. It can be positive or negative. If it's positive to the right, negative to the left. Also, this pole has the velocity, right? The angular velocity and the angle of from the shift detecting the anger from this upright position. Okay, so the sensor information, the state information we have for this problem, usually we have these four data types like position, velocity, angle, and angular velocity. Then we can do this parameterized stochastic policy. So since we are using this reinforce, and so we're gonna use the native reinforce, not the AC method, right? So we have this state, then we put into the neural networks. So like mostly we just use two layers. Okay, we will look at later. So the output layer will be the softmax, will generate the probability for either left or right, the two actions, right? From 0 to 1. So then these are stochastic policy for A1 or A2, left or right. Then the policy pi theta st is parameterized inside of these neural networks. So if we look at then before we starting designing this this learning process, we need to know what is the action space. Also, I need to mention that here, when we consider this problem, actually the action space is discrete. Okay, only have two actions, A1 or A2, left or right, is the discrete action space. Then here we can see here. Also, you see the action space. There's two actions: there's a push left or push right. Also, here we don't consider the force. The force will decide the speed, the acceleration, and we just consider the fixed force. The observation space, the four observations or four states data, four states the information, position, velocity, angle, angular velocity. They have this range, minimum and maximum. The starting state in this cut pole environment, the starting state is defined as when it stands upright there. So our task is to maintain that state actually. So the starting state will be the assigned uniformly random variable in this. I guess this is the position is minus 0.05 and 0.05. Oh, I think this is the range for every this velocity. They are all in the zero, around the zero state. Okay, so it means that the position is around zero, velocity is also around zero, pole angle is also zero, means it's upright, right, standing there. The velocity is also zero, close to zero. Then the ending conditions it's like we have if you have this angle is greater than the 12 degrees, then it will just terminate. Means that the pole will fall down, right? Then the cut position is greater than the 2.4 meters, means it will move out the range, the current environment. Truncation episode length is greater than 50, means that you have a very long time steps. So it's just too long. We just stop there. Just consider it's the end of the episode. The maximum episodes time step is 500. Yeah, the three conditions, okay, will decide whether the episode ends or not. Another environment is inverted pendulum. Actually, similar to this cut pole. One difference is that the action space, previously I mentioned, I highlight here, the force is fixed in this cut pole environment. But in this inverted pendulum, the force is not fixed. Actually, the force, we can only decide, we want to learn this force. So the force will be falling between -3 and 3. Okay, the range means that this action space, which means this action is a continuous action, right? Continuous. So there will be no like a discrete. You can discretize it, but we're gonna use just continuous action space to learn the policy. So it means the -3, -2, 3, you can be the 2.9, 2.1, 1.5, the fourth, or left or right, right? Yeah. So this is one major difference. Then observation space is similar. We have this position, the velocity, angular velocity, the angle, vertical angle, okay, similar. Then dimension. So yeah, and the reward is the +1 for each time step when the pole is upright. It's a kind of maintain that state. This is another environment for a similar environment in the gymnasium. So for this environment, if you see here, there's another like a description of this. You can do the left or right, and the point is here to control this pole. And actually, we can solve this issue based on the dynamics. Okay, so there are already some people, some researchers, they so this is the inverted pendulum. So you have initial state, and so this is the starting like state, the ending state. So the optimal trajectory for this pole should be looks like this way. So if you look at the time step, each trajectory is equally uniformly distributed. So you see here at the beginning the speed is low, but from this time step to this time step, the cart moves a lot. It means that it has a high speed or accelerate its speed, right? So from the starting state, it's moved to the right and it accelerates. So this pole will be like swinged to the left and then suddenly stop at this state. Then because of the inertia, the force, this swing, this pole will be swinged up to this somewhere here. And at this moment, then these cards need to move back, okay? Need to move back, give additional support force to swing it up to the upright. Then so you see the process starting, the move, accelerate to some point, and the retreat to some point, give the extra support for this pole to upright, then move a little forward, then eventually this pole kind of standing there upright. So this is the trajectory, the optimal trajectory for maintaining this. So if you check this research paper, it's like tutorial about how to derive this optimal trajectory. They have a lot of dynamics for this how to do the acceleration and the velocity and the angular velocity, their relationship. What is if you do how much the acceleration, the angle of this angular velocity of this pole will change how much. So they have this interrelated dynamics. So if you solve those dynamics, you will get this optimal trajectory. Then actually in the reinforcement learning, our goal it will be to approximate this optimal trajectory, right? Also, if you check this tutorial, you will see that those dynamics are quite complex. So they have a lot of math, okay, a lot of equations. Then you need to, each time step, you need to calculate those equations and get some result. And each time step, you need to decide what kind of force, what is the speed this cart need to be. So you need to base on those dynamics to calculate. Yeah. So in our case, we use this reinforced with neural networks. In specific, we use two fully connected layers, FC1, FC2, as is shown here. So we have this input, as I showed you. I don't maybe this is a position, this is the position, the degree, I don't know, yeah. Depends on how you define it, right? So you have this tuple, the input tuple, the sensing information or the state information for the current agent in this environment. Then you put into this shared FC1, so the first layer, then the second layer. The second layer will output the, so one thing is that we are using we will generate action probability distribution instead of the probability for each action. Why? Because in this case, so actually we are considering this inverted pendulum case because the action space is continuous. So in this cut pull, the action space is discrete. So it just has two actions, either left or right. We just need to decide. So the softmax will just generate the probability for each action. That's good enough. But in this case, we need to generate the probability distribution for the action space. So it will generate between -3 to 3 in this range. What is the best the force to be applied on this cut? Then it will reach the desired state. Okay, that's why we put the output will be we use the normal distribution, Gaussian distribution. The output will be mean FC and standard deviation. It will generate two parameters, and the two parameters will decide an action probability. So the action probability has the mean, right, and the standard deviation. The mean will decide the optimal force to be applied, right? Then we can, after generating this probability, then we can sample some actions, sample the force from -3 to 3. We can sample a force from this generated distribution, right? So this distribution will be trained again and again through those multiple episodes, right? You can just try an error and try an error. So multiple times, then eventually you will have the trained parameters in these neural networks. Then with these parameters, the trained parameters has reached some good performance. Then you just give an input, it will generate a probability distribution for you. Then if it reaches to some like optimal state, then the probability distribution should be located somewhere that's close to the optimal force. Okay, the mu should be close to some optimal force, and it also may generate some confidence for this distribution, for this optimal state. So if it's low confidence, it will have larger standard deviation. If high confidence, if it's small, right, it will have very sharp peak of the probability. So this is how inside of here, inside of these neural networks, we use 10H as a activation function in the FC1. And we also use 10H as the output probability distribution. Because the reason we don't use in the previous here, if it's discrete, we use a softmax. Because softmax will generate the probability between 0 to 1, right? It kind of fits the probability for the discrete case, action space. But for this inverted pendulum, this continuous space. So actually the generation, the output should have a larger range. That's why we use 10H. The 10H will generate from the negative to the positive, right? It covers from negative to the positive. It covered both sides. Yeah. That's why we use 10H to generate the mean and the standard deviation. So from source code level, how you can run this. So just as a reminder, we have this reinforce the algorithm. So actually the algorithm itself is simple. The thing is how we can run it. Actually, as I mentioned in the previous algorithm in the DQN, even though the algorithm is written in this way, actually each component may be designed as a function. So when we run, there's a main process, and each component has their internal process. and we just call those functions here to update. Especially for the theta update, since it's a neural network, you need to define the network structure, right? So it's the network structure, the multi-layers, if the dimension, input dimension, output dimension, all those information need to be specified. Usually we define a class for those one, right? You can derive it based on the PyTorch, the class. So we first take a look at the source code level for this policy network. The policy network is about how we can update these parameters, theta here, okay? So, yeah. So as you can see here, the running G and GS, the running G is the every time step, the accumulated return called running G. Then GS is the just save those running G. Every time step, we save those data into this like accumulated, each time step has this return, right? So we have this reward. So in the class, so here I just give the self this reward. Then we iterate from the n to -1. We iterate from the end of the like if you remember the MC, right? We reverse from the end, then move to toward the beginning. So yeah, from here. Actually, for calculating this G, we reverse from the last state, from terminal state t-1, and then move back to calculate this return. So for this return, a reward in this reward, the trajectory of this reward, right? Then we just plus R plus the gamma, the discount rate, right? Times the running G. So this gamma, actually here we did not use the power to reduce the gamma. I guess the gamma here is very small, so that's why they don't use this I mean the kind of reduce the power to the gamma. Then you just add them together to the running G. So the running G is from pre-step. So it's like the RK will be accumulated, right? Here. Then we insert this each time step, we put those running G to this list, GS list, to at the first position. Okay. Then we convert it to the tensor. It will become a delta, which is here, right? Delta in this case, the delta. Okay, which is G. So because this G, this return can be different return, can be TD, can be unstep TD, or any other, right? So usually we use the delta, right? Yeah, we use delta to represent. So this G will be delta. Then we use deltas to represent this G. Now we just calculate this the loss function. Okay, we generate the probability and delta. We put them together. And then actually the self probability this will actually will sample the probability, the action probability from the current state, and we use the log, okay, which will exactly run this one. The gradient log length pi this generate the probability. Then we put this log probability mean times the delta times the -1. So we use the -1 because if you remember, when we derived the policy gradient theorem, we actually use the ascent. We try to improve the performance, but generally in the neural networks we try to reduce, get the minimum. So that's why we put the minus and reverse the learning the direction to the descent, not the ascent, right? After that, we can run this. We optimize. No, we initialize the gradient in the optimizer. So here optimizer is the one you can specify. It can be Adam, can be any other, or natively the SGD. Okay, it's from the those PyTorch or TensorFlow, Keras, they all have different kind of optimizer. Then you use the backward and step. So through this process, the parameters will be updated. Okay, this is the implementation, source code level implementation of this parameterized, nonlinear parameterized the update for this theta. Next one is the structure of the neural networks. So as I mentioned here, the structure. So there will be input, the dimension, the input to these neural networks, FC, the first layer. The first layer, the input will receive the 4 dimensions, right? The 4 data. Then it will use the 10H as the activation function. So the thing is what is the dimension inside? Actually, the dimension inside of this, as long as you fit the input dimension, the internal dimension you can define by yourself. It can be 16, 32, means that how many nodes are here, right? So if you higher node, you have a higher computation overload, like a load, or you may have a higher finer approximation data, but the training time will be longer. So in our case, actually I didn't specify so we define it, we use the NN PyTorch class, NN class, the sequential, we just define the sequential, linear, and 10H. So after the observation space dimension, we give this dimension, which is 4. The hidden space 1, you can specify yourself, 16 or 32, usually like this way. Then after that, this linear combination will be activated by the 10H. Then after 10H, we'll go to another hidden layer. So now the space 1, the dimension of hidden space 1 and hidden space 2, they also should have the input dimension, the output dimension should have those the column size and the row size should be the same, right? Because they need to do the matrix product. Then the output will be 10H. So now we just define this the first, the shared network, which is here. I think the FC1, FC2, they're both sides are already defined in this structure. Now we need to specify the output layer. So the policy mean and policy standard deviation. So the output layer will be you will generate, you need to specify the action space dimension. So which means that what is the dimensions of the space? Actually, we just have one dimension because it's continuous. But actually we use actually it should be 2 dimensions, right? Because we use the Gaussian distribution, it has 2 parameters, mu and the sigma. So it's 2 dimensions. The output should be 2 dimensions. Then yeah, similarly here. So we just specify the output layer. Then we just combine them together. This shared net, which is from here. Then we give the input. X is the input layer, which is the state. We have 4 numbers, 4 data points, right? Get the input to this. Then it will generate this is just the object of this class. Then we put this object to the output, the output layer. So this input layer will be the output layer from here, right? Linear, and it will generate the output dimension. So eventually it will generate the means and standard deviation. So here we use the log 1 plus. So you can check the detail. Because here we use log, the reason is that it should not be the negative, right? It should be positive. We use the log to represent the standard deviation. So this is how we can implement this continuous space. Okay. So as I mentioned, that eventually it will generate after many iterations, it will generate the mean and the standard deviation, which corresponding to a normal distribution. Then whenever you have a new state, then it put into the network, policy network, then it will just generate the mean and the standard deviation. Then we just sample, we just get if you just try to do the greedy, you just get the mean, select the false with the mean value. If you want to do some sample the data, you can sample the data from the distribution. Mostly we just do the sample because we don't want to lose some, because this reinforced naturally, so the continuous space, naturally they have this exploration feature because we are generating the probability distribution, right? It already has the exploration feature. It can help to explore different kind of possibilities. Yeah. So yeah, any questions? And the full implementation you can find from here. It's from the tutorial of this gym. Okay, if you click the link on the bottom, you can click, then you will see the whole implementation. Yeah. Yeah. So training using reinforced for multi-joint this like the scenario or environment. So they have a lot of description, how you use, how you can what is the library you're gonna use. So the policy networks, the agent, this is exactly algorithms, the reinforced algorithm. We didn't add the bias, right? The baseline. We didn't add the baseline here. And the reinforced agent sample the action based on the current distribution, right? And update is the one we in the algorithm I showed you how you can update the algorithm, update the theta, right? Then eventually you run the main process. Then we'll call those we'll use the object of those class. So this is the main process. So you build the environment. There is a wrap. So it kind of try to record this, save some video clip. And the total, the number of episodes, you just truncate the maximum episode you want to train. Then this is dimension. I mentioned that the dimension so the dimension is from the space, right? Observation space, which is the state space. Then action space is output. So we have two actually. There is the mean and the standard deviation. So actually, one thing I need to mention is that the seed. So based on my knowledge, the seed actually quite important. So usually when we run the simulation, run the algorithm in the reinforcement learning, we need to check different seeds. Sometimes if you just try one seed, the random seed, that means that those trajectory, those data, the random number generated based on this particular seed may not show a good performance. But if you try it from another seed, then it may have a good performance. So most of the time we try different seeds to see whether we have those kind of issue. Okay. Now this is the main process. How you can do, and you just I taught you to set all those seeds in those pseudo-random process. We build this agent based on this reinforced function, by the input and output, the policy network, right? The reward over episodes. Then for now, for each episode, we need to run how many episodes we want to have. Then we reset at the beginning. For each episode, we reset all the environment information. Then just run based on this environment. So we sample the action. Then we do one step. We put this action into the one step. It will generate the observation, the new state, and the reward. then we save this reward for the future use. Then the condition, the termination or truncated condition is that when we finish this episode, right? Then we just check whether this done is true or not. It's just for the saving the data to save for the plotting, right? Later we want to plot. Then agent update. Then this update will do the reinforce update process. It's like you accumulate the return. With the return, you optimize the theta, the weights vector. Okay. Each time just print out information. Then if you run this process, it will take some time to finish because it did not use the GPU. So because when we run here, when we save the data, we didn't use GPU. So the running process will be put on the CPU. So it's kind of a little bit slow. If you want to run it, you can rewrite some part of about torch, put the data into the GPU instead of the CPU, the memory of the CPU. So eventually, if you run the plotting function, the plotting function is just get the data from this reward to plot, which the data we saved from this rewards list. They just combine these rewards, reward of a list. So the data we saved here overseas, then we just access those data and put into make it become a data frame and give some different column the name. Then eventually we can plot. You will see the performance of this inverted pendulum. You see our reward should be so our setting in here is that the +1. If you keep the pole upright, then they will have a +1. So it means that at the beginning we have very low the reward. When the time step or episode grows, then we have a much better the reward. Means that at this moment, most of the time the pole is kept upright, right? This is eventually the training. So after this, the neural networks you trained, it's already you can, if you want to use it in another, it's like a pre-trained neural networks, right? So after this training process, the parameters inside of these neural networks, you can save those models. The next time you can just load this model and give the input, they will generate the distribution for you. Then you can sample the distribution. Yeah. Any questions? Okay. I just hope you are doing well in your term project. And next Wednesday is the deadline, and you need to submit your report and the slides, source code stuff. Okay. Okay, so this is for the two examples. Let's come back to so now I just tried to give you some like guideline or instruction about the term project report, how you can write the term project report, right? So okay here. So this is the template you received, right? Then you put your term project title here, the one you specify in your proposal, you design in your proposal. You can put here, I mean, you can update the title, even though it's maybe different, but mainly you should keep the similar meaning, right? And you put your team members' name. Maximum you have 2 people's team, right? You can put your 2 team members here. If you have just 1 person team, you just put update your name, the information here. Then this part you can delete. So one thing if you use this Word template, MS Word template, when you try to modify something, so you can show this, switch on this the marks, so the formatting marks. If you switch on, there's a marks here. You will see the formatting, those locations. Actually, you see that they divided this the template into 3 sections: the title section, also section, and the main section. So just in case you messed up the format, so you will see where you should delete. Sometimes you will delete something, you may delete some like a section break, this kind of information. Then you just totally mess up the template. For example, if I just try, if I delete some, okay, let me delete something. So for example, here I just added the one enter, then it's kind of the 2 authors information are shifted. Okay. So actually here, in this author section, it was designed 2 column, as I remember. Layout set. Okay, actually use 2 column here. If you want to switch to one author, you can switch to 1, then it will be easier for you. Otherwise, there will be some. Then you can just delete this part. It will be easier for you. Okay. So then, similarly, here is also 2 column. If you select it, you will see. Oh, okay, here I cannot see it. Yeah. Okay. Here it did not show it's a 2 columns formatting style. Yeah. Anyway, so it just when you try to format your paper, your term project report, you can check from time to time. You can check those formatting symbols marks here, just in case you messed up the formatting. Also, so each of these title, the section title, has the formats, the design. Let me see. Here, the styles, the heading 1, heading 2, heading 3, they have different for the level 1 section should be using this heading 1. Okay, they have different heading. The subsection should be using the heading 2. So they have different levels. And yeah, so this template is a general template. Okay, general template. So there are a lot of instructions. When you write your term project report, you need to remove these instructions. Okay, you just leave your contents, your own writing, and you may need to add some mathematics, some equations. You can use the native equations from the math, or you can use another like a math tab application to input your math equations here. Another one is that if you want to input the like algorithms box, right? Sometimes you see those algorithm box. Then you may use, for example, here you can delete this, you can put the insert, I cannot see okay, just at the home. So there's an input, we can input the text box here. Shape. Yeah, okay. From shape here, you can input some like rectangles or just directly this text box. The text box is a little bit, but it's like a floating on the text. So you may need to select this wrap text with this top and the bottom stuff. Yeah, now this box is embedded into the text. Now you can write some like algorithms one with some, then you need to switch back to from the beginning. Algorithm one, let's say Monte Carlo, the Monte Carlo methods. Then, so I always did not automatically, you need to maybe, yeah. So you can also change the font, right? Make it smaller. Then you can like the input stuff, then some like parameters stuff. Then you can like you can just follow like for something A in B something. Then you need to put the tab, but by default tab is 8 spaces, but it's a little bit too large. You may use just 4 spaces, 1, 2, 3, 4, and to type this. Or yeah, this is how you, if you want to make your algorithm looks good. But yeah, in the textbook or in other research papers, when we input the algorithm, we usually use the LaTeX. So the LaTeX, they have the packet to generate different style of algorithm. Okay, it will be much easier. So we just need to input this particular the information there, and then it will automatically generate. And you can also input the figures. There's no figures here, right? So, but there's the instruction how you can input the figures. For example, here, this box gives you some instruction. You can use the text box to insert a figure. So similar to this algorithm, you can just insert a figure, a graph, input the picture here to cover the graph and give some caption. And yeah, any other questions if you have? So for, as I mentioned in your assignment, the submission page, for the single person team, you need to have at least 3 pages for this template. For two people team, you need to have 4 pages, right, of this template. So to describe your project, which means that 2 people's team should have more work than the single person team, right? So, any questions? Mm-hmm. The within 10 minutes, yeah, the presentation 10 minutes, yeah. So especially how you can write this. So at the beginning, I already write some abstract, the instruction for the abstract and the instruction for introduction. So especially there's a multiple points you need to mention, and also background. They mention some related approaches, methods here to categorize them into multiple subsections. Then eventually your main focus should be on this method design, which method you are using, and you need to detail the method you are using to describe how the method works. Is there any equations? You explain the equations, and what is based on this equation, you have some algorithms. Then also you may need to describe the result. After describing your work in the results section, you need to define which environment you are using. What is those action space, the state space, those termination conditions, all those information you need to describe here. You can use a table to show those information with some descriptions. Yeah. And after that, then I expect that you may have some like graph shown in somehow similar to this one, some graphs like a reward or some like a policy, the probability or something. Yeah. Yeah, depends on your problem setting. Yeah, this is for the Word template, MS Word template. Another one is that I suggest if some of you may use the LaTeX. So for the latex, I suggest you to use the overleaf. If you just open this overleaf latex, and you can register your account, you can just type your account. So I have my account here, so I just directly use it's the for registration. You can just log in if you have. So if you, I encourage you to use the latex. Oops. I suggest you to use the latex if you want to work on some like this AI area, because most of the AI related research papers or work, they use the latex to describe their I don't remember my password. Okay, it's correct. So once you log in, then you have those this you can okay. So on the right hand side you have this, you can click new project, then it will jump out some, you can upload the project, the blank project. You can do they also provide a lot of templates, the academic journal or something here, presentation. So you can use this upload project. Then just upload the zip file I gave you. Let me find which is this one. Okay. So you can drag it here and it will be uploaded. Then we open this one for you. So this is what it looks like, the latex. So you write your paper in this latex. So the right-hand side is the PDF is generated, the similar style of the Word template. Then you can, for example, the conference paper. So the one we are working on is this. The left-hand side, you can see the file inside of this, the zip file. And you can see the structure of this template, the introduction, easy of use. So each top level, this section is the section in your paper. For example, this introduction is here. So let me enlarge a little bit. Yeah. So introduction, then you will see the paper. So you can jump your paper based on this outline anywhere you want. For example, I just want to change the title. So there's a lot of information here. You just need to search the title. So this is abstract. So the beginning abstract and end abstract is located here. So you see, this is the document. This document is a model, and this document is model. So you can write the text here. But I mean, if it's the first time for you to know this latex or overleaf stuff, you can check some tutorial online. It's not that complicated. You can, while you are using, you can learn. So while you're using, you are learning. So if you don't know something, you just check those different kind of sources. For example, if I just want to change the title, here the title is a conference paper title, which is located here. Okay, the title. So if I just change it, you automatically change. So for example, turn project report. Now after changing this, there's a recompile button. You just recompile. Now, so the PDF is generated, so the updated term project report. Okay. Then you can also specify update the name, the author information. Author is from. So there are 6 authors. They give the 6 authors. You can delete. You just leave 1 or 2. Then put your name. For example, here given name and show name. So like my name, I put my name here, and I recompile again. So my name will be updated here. So you can just follow this style. So you may be wondering, what are these authors? It's just some anchor, the formatting information predefined. You don't need to worry. You just need to replace those texts information. So the format is already predefined. You don't need to modify it. So yeah, and also it's how to input the math equations inside of LaTeX. You can also check related tutorial. It's good to use. Even for when I generate the lecture slides, I use the LaTeX to generate those equations that I screenshot and put into the slides. Because if you type the equations in the MS PowerPoint or Word, it's kind of burdensome. Yeah. Okay. So this is the LaTeX, but I encourage you, maybe it's the first time for you to know the LaTeX, but if you want to work in computer science area or like AI areas, future, I suggest you to be familiar with the LaTeX environment. And also this overlay is for free. And actually there's if you search, I mean, there's an advanced version you need to pay, but basic version you can just use for free. Yeah. But later on, if you work with some other big team, you want to collaborate together, like you can just send your email, share this project with others, so multiple person can work together online, real time, for this product, for this particular project. They will receive, they will join, then for example, you update your title, then the other person can update the other instruction area, the online collaboration. So this is for the LaTeX, the template. Yeah. So the one thing is once you finish, if you use LaTeX, you finish, then there's a download button. You can download the PDF. So when you submit, if you use LaTeX to write your report, you need to submit both the packet, the zip file. You can download the zip file from this menu, then download the source. It will download the zip file of your current project. You can also download the PDF. This PDF will be similar to here. The download here. We will download the PDF, the current, the compiled version, and to submit. Yeah. So this is the LaTeX version, and so about the template of the slides, I also showed you, which is based on the template I'm using. Then I also specified multiple sections. It basically just follows the structures of your report. So like problem, introduction, problem, motivation, methods, and the results stuff. Yeah. Okay. Any other questions? Okay. What else I want to share? Okay. So yeah, I guess I just had I don't know if I just don't remember it's something I want to share. Yeah. Anyway, so if I have something to share with you for this term project stuff, I will send some announcement or notice in the iCampus. Okay, later. But yeah, next Wednesday is the deadline. Before that, you need to submit. Okay, that's a firm deadline. If you delay that, I don't have enough time to check your submission, right? I need to use one day to check your submission. Then Friday, I need to do the presentation. Okay. Yeah. Okay. Any other questions? So if you don't have a question, then we are done today. Okay. And see you next week. Okay.